All right, boys and girls, let's get started.
Is it going to be like 25 or is it going to be like 70?
Not 70 today.
Not 70. Okay.
Yeah, no, we're only going to go up through section 4 today. All right, so I'm going to go through a few of the introductory topics on chemical equilibrium today. There are going to be some homework problems for you to do over this information. If I get done early, you'll have time to work on those homework problems. But we will also talk a little bit about how to write specifically equilibrium expressions, which was your daily cue for today. Anybody remember how to do it? Or does anybody want to describe how to do it? Go ahead, Emily.
Put the reactants over products,
Opposite. Products over reactants.
and then the coefficient becomes a superscript.
Correct. So just like our rate laws, the coefficients in front of our individual species in our equilibrium reactions are going to become our exponents. And we're always going to put product over reactants. We can do this with concentrations or with pressures, and we can get an equilibrium expression. Yes, ma'am?
Which one becomes the exponent?
The coefficients.
Oh.
Okay? So in equilibrium, the very basic concept is that at some point a reaction stops producing and only producing and kind of gets to this point where at the rate that it's producing new substances, it's also moving in the opposite direction to produce the reactants at the same time. Okay, so the forward reaction and the reverse reaction are equal as far as the rate of the reaction itself. You've seen equilibrium arrows before. They are the double-headed arrows that point in opposite directions. And we'll see them all throughout this chapter. But when we see that double-headed arrow, it means that we can do the reaction in the forward or in the reverse direction. And that is where we focus in this particular chapter. So, reverse rate equals forward rate. Next is going to be that as this particular reaction takes place, all reactions that are reversible, if you will, are going to approach some point where no more is being produced and no more is being in the reverse direction producing reactants. We may start somewhere where we have products and reactants, or no product, but definitely reactants. But at some point, we will always reach that equilibrium stage. Equilibrium does not mean the reaction stops. If you tell me that a reaction stops at any point in time, you are wrong. And I will be merciless about it. Because at no point will a reaction ever stop. It either slows down or it reaches a state of equilibrium where at the same time both things are happening. Okay? Never do our molecules just stop. It's not a thing. Okay? When we reach equilibrium, the amount of reactant and product that is present at equilibrium stays constant. Okay? You do have access to my PowerPoint, so if you miss something, please make sure you're following along on there. But when we reach equilibrium, the amount of reactant and the amount of product will remain constant, aka stay the same. It does not mean that one is completely gone or that one is still being created. It just means that we're staying constant at that point. The very end of this chapter introduces the idea of Le Chatelier's principle. And Le Chatelier's principle states that if we mess with equilibrium, it will shift itself to get back to equilibrium. For now, when a reaction has reached equilibrium, the amount of concentration of the reactant will stay the same for the remainder of the reaction, or for the remainder of time that you tend to watch the reaction, if you will. The amount of the product will also stay the same. You will not produce any more or less, unless you do something to the reaction to change that situation. Okay. What we're going to do next is we're going to look at how we get the equilibrium expression. We're going to use a very basic version of a reaction that is reversible. It has a gas that becomes a different gas. The double arrow itself is where you should see that we're dealing with an equilibrium situation. So equilibrium reactions have to have the double arrow for us to analyze them using this particular concept. If you do not see a double arrow, you're not dealing with an equilibrium situation. This reaction has one reactant and one product, correct? And you see the coefficient in front of the product. That's going to come into play here in a second. So recalling from chapter 14, our rate law rules. If we look at this reaction in one direction at a time, we're going to write a rate law that involves the reactant itself times some rate constant, right? Raised to whatever power the coefficient is in front. In this particular case, it's a 1, so there is no coefficient. Does that look familiar? Good. This is the rate of the forward reaction. The next thing we're going to write is the rate of the reverse reaction. The reverse reaction has what species in it, as far as the rate law? Anybody? We take this equation and we write the reverse reaction, rate law, what's going to be in it? You're going to write rate equals K times what? NO2 to the second power, right? Good. There's our reverse reaction. Now remembering that in equilibrium, they equal each other, we can set the rate of the forward equal to the rate of the reverse. And then we can solve for K. There are two Ks in this particular situation. We always put the forward over the reverse when we do this type of a reaction. And I'll remind you that these are both constants, right? So taking one and dividing by the other is the same thing as just writing one of them. The one of them that we are going to write in this particular case is going to be the equilibrium constant, capital K. So our lowercase k's are for rate laws, individual rate laws. Our capital K's are going to be for equilibrium constants. And we're going to be spending a lot of time in the coming months with the capital K equilibrium constant. We're going to apply it to acids, we're going to apply it to bases, we're going to apply it to solubility products, aka when something doesn't dissolve very well. We're going to apply it to pressures and to concentrations in this chapter. This is where we're going to spend a lot of time moving forward. This is the equilibrium constant. Okay? So we're going to take the K, we're going to make it capital, and we're going to say the K for this equation is equal to the products raised to whatever their coefficients are, divided by the reactants raised to whatever their coefficients are. This is for the specific reaction we were just studying. The general form is going to use those A's, B's, C's, and D's that we've seen before. Okay? This is what you were doing in the daily Q, was the products over reactants raised to the powers. Just wanted you to describe it from your reading. This is like section 2 of your reading. Yes?
We can just look at an equation and then come up with that?
Yep.
Because it's going to be the same?
Moving forward, yep.
We don't need to do the whole
Right, so rate constants were there for you to understand that there's a difference between experimental and predicted. These are all going to be predicted equilibrium constants. Absolutely. And you'll see that when it comes down to it, an experiment will follow the predicted method better than anything else. One thing to note right now, we're not inserting temperature into this argument. We're doing everything at a constant temperature. Doesn't matter what temperature right now, we're just not changing temperatures. We're not inserting temperature as an argument. So moving in this particular section, you're going to see things that are like at 25 degrees Celsius or at 300 Kelvin or at 273 Kelvin. Do not worry about temperature and their effect right now or its effect right now, because it's something we'll talk about towards the end of this chapter. How does temperature affect a reaction? We know how temperature changes a rate. We know it speeds something up if it gets hotter. We know it slows something down if it gets colder. But we'll talk more about how that affects equilibrium in the future. For now, we're dealing with constant temperature situations. Okay, so the general form of any equilibrium expression is going to have that capital K, and we're doing this in concentrations for this particular exercise. So the K with a little sub c means an equilibrium using concentrations will be the products raised to their individual coefficients, that's what the little letters are, divided by the reactants raised to their coefficients. Remember, the bracket means molarities. If you do not remember that, make sure you make yourself a note. The brackets mean molarity. Again, this chapter focuses on concentrations in molarity for our equilibrium expressions, as well as pressures. And remember, from the lab we just did, pressure is synonymous with concentration. The pressure of a gas is something we can track as a concentration change. The higher the pressure, the larger the concentration. The lower the pressure, the lower the concentration. So we can do this exact same expression using pressure values. And we'll see that here in a second.
So brackets is molarity, right?
Correct. Brackets mean molarity. And you're going to see these things. Kc, Keq, and Kp. Kc means equilibrium concentration, concentrations, right? Kp means equilibrium constant in pressure. And Keq just means equilibrium constant of the equation. Typically in concentrations when you see it. Keq is like the generalized. Kc and Kp are more specific to the reaction. So this is for my concentrations. This is for my pressures. The same situation occurs. We take our pressures, we raise them to our powers. We multiply we put the products on the top of our fraction. We put the reactants on the bottom. Again, pressure proportional to concentration. Okay. To understand, beyond just writing an expression, how to relate concentration equilibrium constants and pressure equilibrium concentrations, we have to go back to the gas law. And if you remember, the ideal gas law relates pressure, volume, moles, and temperature. In this particular case, we want to relate pressure to molarity, because we want to relate our pressures to our concentrations. If we divide the ideal gas law by volume on both sides, we get moles over liters. Moles over liters is also molarity, okay? So in relating the two, we're going to learn how to take a K in concentration units and convert it to a K in pressure units, using a very simple version of that. Okay, so the first thing we're going to do is we're going to take Kp, we're going to set it equal to K in this concentration form. So we should understand what these two are, right? We know this value is 0.08206. That would be the gas constant. It's not going anywhere soon. T is temperature in Kelvin. Delta N would mean what? Change in moles, ladies and gentlemen. Delta N is described down here. Please get this written down. Please. Moles of product minus moles of reactant is delta N. So this is how we can convert from Kp to Kc or from Kc to Kp. If we knew one of them and we wanted to calculate the other, we need a few pieces of information about the reaction, but other than that, we can do this concentration conversion. Yeah?
What is the difference between Kp and Kc again?
So Kp is the equilibrium constant in pressure, so ATM, and Kc is going to be the equilibrium concentration in molarity. Our goal is to go from molarity to pressure or from pressure to molarity, depending on the situation. To analyze equilibrium, something to understand is we can go either direction. If we start with reactants, a lot of times we think of reactions as only moving in the forward direction. In reality, the way that I write a reaction doesn't matter when it comes to equilibrium. What matters is that we can go from either side to either side. So I can start with product and I can go back to reactant. I can start with reactant and I can go over to product. Does not matter which direction I'm going. The principle remains the same. However, going forward or reverse does impact your value of K. And we're going to look at how that works next. Okay? When it comes down to it, it's a very simple manipulation. So a lot of what we're learning in these first 3 or 4 sections is manipulating K after learning how to write K. So just like we talked about with rate laws, there's very specific ways that we can mess with our constants. We can look at them experimentally and we can say, okay, from experiment 1 to 2, this thing doubled while this thing quadrupled, so the rate order must be 2, which helps us write our rate law. This is a little bit different, but in reality, if we look at experimental data is going to show us that no matter which direction we approach from, if we start with the same amount, we're going to end up at some equilibrium value. And that equilibrium value is going to be determined by how much of whatever you started with existed at the beginning. Okay? So in this particular reaction, we're looking at the concentration of NO2 on the left side. We started with the product from that original reaction that we wrote, where we had N2O4 become 2NO2. I'll remind you of that reaction. In this particular case, we went the reverse direction and started with the NO2. And the N2O4 is the thing, and then in a different experiment, we started with none. Okay? So starting with NO2 led us to some equilibrium concentration. Starting with none of it and just N2O4 still led us to that equilibrium concentration. What they're telling you is no matter which direction you work from, equilibrium will still apply. Okay. It does not matter when it comes down to the equation which direction you're going. What does change is the value for K. And we're going to learn how to go from the reverse K to the forward K and so on and so forth. In this particular reaction, this is the Born-Haber reaction, where we take this particular reaction, depending on what we started with. In this particular case, it looks like we started with H2 and N2, and we had no NH3, so this is the forward version of the reaction on the left. We eventually reached some concentration that was equilibrium, right? Over here, we started with NH3, and we didn't have any N2 or H2, so we went the reverse direction, and our reaction concentrations are the same at equilibrium in both cases. So it does not matter which direction you go, equilibrium concentration should be the same for whatever concentrations you start with, as long as they're molarly equivalent, and the temperature remains the same the entire time. Okay? This is just experimental data that proves what we're saying about equilibrium concentrations. Okay. Now we have to interpret what K actually is, because K is going to be a number. You plug in a bunch of concentrations, you're going to get a number out of that equilibrium expression, right? If K is a very, very big number, it means your reaction is called product favored. So if K is much bigger than 1, very, very, very big number, then your reaction is considered product favored. Say we wrote an expression for this particular reaction, the way that we've written it, K would be a very big number. It means that this reaction prefers this to be the thing that's in dominant form, present in the largest amounts, if you will. Okay? If your K is a small number, negative exponents, if you will, then your reaction is going to be reactant favored. It means the reverse direction is the thing that's the most common. Means your products tend to be there in larger concentrations. And if you think about the actual expression for K, we put products on the top, reactants on the bottom. If you end up with large concentrations for products, yeah, your number's going to be big because the number on top of the fraction is the big number. the reverse situation, where if we have really large concentrations for reactants, that makes this fraction very, very small. So when we say reactant and product favored, we're just looking at the value of K. You will see Ks with very, very small numbers. You will see Ks with very, very big numbers. You will not see K equal to 0. Why?
Does that would mean that one product or reactant is not being formed at all?
Correct. That would mean that something isn't happening at all. And we just talked about how that never happens. If you write a reaction, we can say the reaction goes to completion, but if we're talking about a reversible reaction, that means that at some point, all of our concentrations leveled off. In a reversible reaction, nothing will ever be 0. So your K should never be 0. Does that make sense? Now, if I did something like I'm balancing in my head. If I did something like this is a single forward reaction, right? Could at some point one of these two things run out? Absolutely. And if it runs out, it's at 0. So could K exist for this? No. For a lot of reasons. One is we just talked about the rules for equilibrium constant expressions. For equilibrium to exist, what do you have to know about the reaction? It has to be reversible. There is no equilibrium here. It's done when it's done. When one of the things runs out, the reaction is over. So if you aren't dealing with a reversible reaction, you shouldn't be talking about equilibrium. Okay. If we want to manipulate our equilibrium concentrations, let's say we wrote one version of our reaction. Remember, we can write the reverse. So this is the forward, this is the reverse. The K value for this first one you're given is 0.212. If we want to know what the K is for the reverse, all we have to do is take 1 over this number to get the K. So, in your notes, it will be helpful if you write if you want to reverse your reaction, you want to know the K of the reaction. So you want to know what Kr is, you would do the inverse. So K of the reverse reaction will equal 1 over K of the forward reaction, if you will. You probably don't need the first one. I'm going to rewrite. That's the first K manipulation we can do. Remember, we also said that we could manipulate Kp in a previous slide. Make sure you have that written down in your notes as well. Okay. In particular, another thing that we can do is if we multiply the entire reaction by some number, we can manipulate K by raising it to that power. So for instance, up here we have the reaction. We know what the K value is. Here we've doubled both sides. Do we see that? What we can do is we can take the equilibrium concentration raised to the same amount that we multiplied the whole thing by. So there's another manipulation for K. I don't really know how to write that in a simplified way. Make sure you have that written down. If I had multiplied this by 3, and this was a 3 and this was a 6, I would raise the power to 3. Whatever you do to the reaction, you can raise the power of the K. The first question on your homework has you just writing equilibrium expressions. So So products over reactants raised to the powers if they're balanced, etc. A couple of the other problems have you manipulating K based on the information you're told. Here's the forward reaction. What would the reverse K be? The K is this number. Does that mean it's product or reactant favored? Yes?
For that on the board, is that a negative or is that a bracket?
It's a bracket. This one?
Yeah.
These are just brackets.
Oh.
Products over reactants. Or pressures, whichever. That was just general form of K. All right. I have to introduce Hess's law again. If we have a multi-step reaction, okay, all we have to do, let's say we have this. Okay, so we have reaction 1 and reaction 2, and when we add together, we get the sum of the reaction. Okay? If we have a K for this one and a K for this one, then the K for the whole thing is just the product of the two. In the past, we've taken two reactions, added them together. We had delta H values. We added the delta H values. For K values specifically, they are multiplied. Ugh. Ugh. All right, that is all I have for you today as far as your lecture is concerned. Here is the homework you are assigned. Like I said, number 16 has a lot of them, but all you're writing are equilibrium expressions for this. So practice writing your K expressions using the products divided by the reactants. That's all you have to do for that one. Okay? Another thing it says is in each case indicate whether it is homogeneous or heterogeneous. What does that mean? Go ahead.
Homogeneous means it's like all one thing, so it would be all
All gases or all solids or all liquids or all aqueous would mean homogeneous. If it is not all the same state of matter, then it is a heterogeneous equilibrium situation. Okay, so that's a simple addition to this particular section. All right, down here it says which of these lies to the right, meaning product favored, which of them lies to the left, meaning reactant favored. What do you need to interpret that? The K values, right? We just talked about this. If K is greater than 1, it is product or reactant? Product favored. If K is small, then it's reactant favored. So all you have to do is interpret K's. Down here, you're given an equilibrium particular thing. It says calculate Kp given Kc. For that, all you need is the temperature that it's done at, which you have. How do you calculate delta N? That is something that we mentioned. Moles of product minus moles of reactant. When we say moles, we mean coefficients. So add the coefficients of the products, subtract the coefficients of the reactants. So in this particular equation, hopefully you can see it, how many moles are there on the right side? 2. How many are there on the left side? 2 plus 1 is 3. Okay? All right, then down here it says 2 equations add together to give this equation. What is the K? Okay, and we just talked about how to do that. All right, get to it. You got 10 minutes in class to work with it and ask questions if you need it. 4 more problems. You can do this. I mean, you can opt not to do it and take a 0.
You should get rid of the numbers, just make it one problem. Be like, we only have one problem for homework, and then you show us this. That's hilarious.
I've done it before.
I know you have.
Try that again, just to make sure.
Take you 30 minutes. 35.
35 much.
35 minutes. Maybe 40.
40.
Depending on how quickly you do the math. In the last ones.
So more stuff.
This one isn't even math. This one's math, and this one's math, and this will take you 25.
My staff can work out awful.
Please do pay attention. If it says KP, you probably have to do the KC to KP conversion unless you were given concentrations and pressures. Hmm?
I don't want to do this calorie weight.
Yes, ma'am. Yeah. You say, can I go to the bathroom? Hold on 1 second. I'm just gonna let you see this board for a second. And then I'm gonna erase it. What's up?
Okay. How do you know for
So it's homogeneous if everything is in the same state. So for all gases, it would be homogeneous.
So it would be like.
Correct.
Okay.
These are the states of matter. If it's not, then it's
Okay.
heterogeneous.
Oh, I get it.
Yep.
Yes, sir.
Yep. Yep. Good question. Hey, boys and girls, what are you supposed to do with solids and liquids in your equilibrium expression? Ignore them. Gases and aqueous things are the only things that matter.
So you just wouldn't write them?
You
Yep.
just, so like for B, you just write, you don't write the.
Right, so it would just be 1 over CO2. Right?
You're so hard.
So your B?
Oh.
Yeah. So 1 over CO2 squared.
So, yeah, that's good. Well, it's O2 cubed. So it's raised to the power after. Does that make sense? Okay.
Solids and liquids don't have any gas. Meaning they don't go into your expressions.
So you just not put them in. Okay. Just pretend they don't exist. You only do gases. You only use gases or liquids? There's only gases. Yeah. Ignore them. Put in a 1.
Oh, there's 2 of them.
Getting started? So ignore solids and liquids. Okay. Write it down so you don't forget. Ignore solids and liquids.
So even around the food, it's still.
Correct. Well, yeah, because it's part of it. Yes, sir.
That's probably about.
Sure. First one? I mean, that one looks okay. That's O3 cubed, right? Or I'm sorry, O2 cubed and then divided by O3 squared. Products of the reactants, so it's right. So this is the product, right?
Yeah.
Okay. So, yeah.
I just put K of
You didn't have to do anything other than just interpret the K, right? Since it's a big number, it must be product favored. And since KC, bleach or dust? Can't tell.
I don't wear like.
Someone who literally.
Probably bleach. It's all good. It's all good. Probably gonna use bleach for ourselves. Yep. You're right. Which one? Remember, you ignore anything but gases. So for B, it should just be 1 over CO2 squared. Ti is a solid. And then for D, it should just be the CH4 over H2 squared. Yep, that's good.
That's how you write ones where there's one product or reaction.
Times. Okay?
But you would still write heterogeneous.
Yes, because it's still a heterogeneous equilibrium. Well, no, it gave you K.
Oh, well, I thought.
You just have to interpret if K means it's product or reactant favored. So since that's a big number, what does it mean?
It's
Do you remember? Product favored,
Okay.
correct. And then the small number means reactant.
Yeah, okay, got it.
Yep.
Thank you.
Yeah.
Ignore aqueous.
No. I put them.
So yeah. It's the K. For that one was -1, right? Yeah. 2 minus 3 is -1. So you're gonna do RT to the -1. Does that make sense? Yes. Okay. Nice. So it should be just a little smaller, Kelly? Okay. You ignore the solids and liquids.
Okay.
But that means that it's probably still heterogeneous if they're in there.
Okay.
Does that make sense? Just because gases are the only thing that make it doesn't make it homogeneous.
Okay, so the one is.
Yep.
Okay.
So whenever you don't have something, you always put a 1 in.
Okay.
So then for this one, for C, you got the reactants on the bottom, good, and then you do the products on the top.
Yeah. Okay.
Yep. Always remember, products on top, reactants on bottom.